Sorry about that. I think it's all working now. Thanks for coming. So I guess a couple of brief announcements. So hopefully everyone saw that the homework deadline got pushed back until Wednesday night. So you have a couple extra days to do it. So it doesn't leave us a ton of time to have a fifth homework unless I assign it so that it'll be only available during the study period. So instead, what I might do is release essentially like just like kind of a bonus assignment that you can use to basically apply to one of your previous homework assignments in order to boost your grade if you're interested, but it'll be purely optional so that you don't there's no disadvantage to not doing it other than you won't be able to apply it to a particular homework assignment. So that's what I'm thinking currently, just so some people that maybe messed up on one of the earlier homeworks will still have a chance to make up some of the difference with their by doing a little bit of extra work. Same kind of update with the final. So again, it'll probably be it'll be a take-home exam, and the plan at the moment is to sort of release it towards the end of the final exam period, and then have it due pretty close to the maybe on the last day of the exam period, which I think is December 8th. So that's what I'm thinking right now. If anyone has any suggestions about exam scheduling or anything like that, let me know. I could be flexible here. So if there's really something that a lot of people would prefer, I mean, other than we still have to have an exam, but I could be flexible on when it's actually released. Okay. Any questions about homework or exam? The final, basically the final content of the course. Do you know the date of the final? I think it's probably going to be released on December 5th, and it'll be due on the 8th. So maybe late on the 5th, and then due, by the end of the day on the 8th. Yeah, again, I'm going to give like a couple days to do it, at least 2 or 3 days. Just so, I don't know if that overlaps with other people's, other exam schedules. So I'll try to give you a couple days so that you can fit it in. Any other questions about exam scheduling? Okay. So today is really going to be the last of the kind of course content in some sense. So on Wednesday, my plan is just to have a bit of a review day. So please come with questions of your own. I'll probably just pick some practice problems, and maybe we'll just go through them together, just as a way to review for the final. So today's really it in terms of new course content. And just like sort of the last lecture, I picked a topic for today that we in principle could have covered earlier in the course, but I thought would be a good way to just go back and review some of the things that we haven't talked about in a while, and extend them a little bit in some new directions with some slightly new ideas. So this particular approach that we're going to see today is actually super useful in some very restricted settings, and not so much in others. So it really kind of depends. In that sense, it's kind of like projected gradient and Frank Wolf methods. So in fact, it's very much like those things. So we'll see that here in a minute. And it has all the flexibility of all the gradient methods that we've been seeing all along, which is why it's kind of good to introduce it again today. Introduce this topic today. It's a good way to go back and recall some of the gradient stuff that we did earlier in the course, and as we near the end, and add something a little bit different to it. Okay, so to refresh our memory, so with gradient descent, right, the intuition is that we take a step in the direction of greatest decrease, which we showed way back in lecture 2 or 3, I think, lecture 2, I think, is the direction that's dictated by the negative gradient. So that's what we've been doing all along. We've been performing gradient descent. We compute the gradient and we take a small step in the direction of the negative gradient. So if we take a small enough step, we're guaranteed some improvement. The length of the step that we take is, of course, determined by the step size. So the gradient descent algorithm, when applied to minimize a convex differentiable function, works like this, right? You pick an initial point, and you just keep iterating until convergence. You compute the next step from your current step after adjusting by some amount. Okay. And that step size gamma t could either be a fixed step size, right, as we saw very early on, or it could be a diminishing step size, right? So something like gamma t equals 2 over 2 plus t or something. They get smaller over time. So as long as it gets smaller quickly, but not too quickly, the algorithm is still guaranteed to converge to the global optimum, at least of convex functions. So the stopping criteria we had for this, right, was that basically we iterate until the norm of the gradient gets small enough, right? We know that for a differentiable function, our convergence criterion is that we can stop essentially when the derivative is 0, but practically speaking, right, we can never tell the difference between 0 and very close to 0. So we pick some threshold epsilon, and we keep iterating this gradient descent procedure until we get until the norm of the gradient gets close enough to 0. So one little bit of observation is that we can actually reformulate the gradient descent procedure and view it in a slightly different light. So the way that we were thinking about it at the beginning of the course, right, was that somehow the gradient is like the first order, gives you the first order Taylor series expansion, which essentially produces the best linear approximation of the function at a particular point. That's what the gradient does. We can also view the gradient update step, this thing like this, that says that xt plus 1 is equal to xt minus gamma times the gradient of f of xt. We can view that as the minimum of a specific approximation to the function, a sort of quadratic approximation function to the function f at the point xt. So in particular, it's equivalent to minimizing this function over x. So we saw something like this, right? If we were looking at the second order Taylor expansion of a function, it would look like f of xt plus the gradient of f at xt transpose x minus xt. But then the last term, this 1 over 2 times the step size times the norm of x minus x squared, that's not the correct third term in the Taylor series expansion. The correct term would look something like 1/2 x minus xt transpose the Hessian matrix at xt times x minus xt. Right, that would be the proper Taylor series expansion. Instead, the gradient can be, the gradient update that we produce can be viewed as the solution to this other second order approximation, where the second derivative is being approximated by this x minus xt squared term. It's easy to check that the argmin of this thing is in fact that solution, right? We can just take derivatives and see that, right? If you take the derivative of the expression inside those square brackets up there, right? The derivative with the gradient with respect to x, right? Because that's the thing we're trying to minimize over inside the brackets. We get what? Gradient of f of xt when we take the gradient of x, and then plus 1 over 2 gamma times the gradient of this term, which just looks like x minus xt. Now you might say that that doesn't look exactly like the formulation from above, and the point is it doesn't really have to, because the argmin is insensitive to things like multiplying by constants and adding constants. So for example, inside the parentheses up here, we could multiply it by 2 times, or we could multiply by, oops, that's not a 2, it's just a 1 over the step size. When I get the derivative, we could just multiply everything that's inside these parentheses by the step size, and then get the correct expression. Right, by setting this equal to 0 and solving. Of course, right, so solving this equation, same thing, right? We multiply by the step size and solve, and we get that, x, should be equal to xt minus gamma times the gradient of f at xt, as desired. The thing about argmins is that, right, as I was saying, right, you can shift and multiply by anything you want. You can shift by any constant amount, and you can multiply by any constant amount without changing the argmin, as long as we multiply by a positive constant. So this observation is actually the motivation for a somewhat more sophisticated-looking gradient descent-like method called the proximal gradient method. The proximal gradient, the real motivation behind it is that essentially, as we saw when we were having this, the discussion about different gradient methods at the beginning of the course, right? Gradient descent only really makes sense if the function f is actually differentiable. If f is not differentiable, right, then we had to do something else, right? We discussed the subgradient descent method, right, where for convex functions we replaced the gradient with this notion of a subgradient, which was just any linear underestimator at a particular point, and then we iterated subgradient descent. The problem when we did that was that subgradient methods, as you probably saw from the previous homework assignments, or at least you should have probably seen from the previous homework assignments, subgradient methods tend to converge much, much more slowly than gradient descent. Like I said, it's sort of a difference between like 1 over epsilon and 1 over epsilon squared, where epsilon here is if you want to be, accurate to within epsilon, right? The difference between gradient descent for a twice continuously differentiable function and subgradient descent is effectively, it's a squared difference. So if you want to be accurate within 10 to the negative third, gradient descent might need something like big O of 10 to the third steps, whereas subgradient method might need big O of 10 to the sixth, right? So it's a big difference, and it's one that really does it's one that you really do observe in practice. So my students often implement subgradient like methods for solving different optimization problems that come up in the course of my research. When they do that, we definitely observe this kind of phenomenon where the subgradient methods will converge quite quickly to within some region of the optimum, but then take quite a long time to sort of eke out that last little bit of accuracy. For many machine learning applications, it doesn't necessarily matter so much. You don't necessarily need an exactly accurate solution, but that's where the difference in the convergence rates is really playing out, right? Is in really fitting sort of the, that last little bit of accuracy to the solution. So the idea behind the proximal gradient methods is to see if we can design a descent method that has a rate of convergence that's more similar to gradient descent, but could be applied for non-differentiable functions. So let me describe the method. So in the proximal gradient approach, we're going to assume that we have a function of the form f of x plus h of x. And again, both of these are assumed to be convex. So both f and h have to be convex functions, at least in this, if you want this procedure to converge to the global optimum. The assumption here is also that f is a differentiable function, but that h can be anything that you want it to be. It could be differentiable, it could be non-differentiable, it doesn't really matter. It's really your choice. Okay. The sort of the most interesting applications, I think, are in the non-differentiable case, but there's also some utility in practice to having a to applying this for a differentiable h as well. As we'll see in a minute, the choice of h can greatly affect the way that the descent strategy makes progress in space. So sometimes there is a real benefit to breaking it off, even if it was a differentiable function. So here's the motivation behind the proximal gradient method: is that since our assumption is that f is differentiable, whereas h might not be, when we do this if we view gradient descent like we did in the previous slide, as basically solving an optimization problem by applying a second order approximation to the function, well, what we could do is say, well, the function is differentiable, the function f is differentiable, so it makes sense to expand it in its second order, but the function h is not, so it doesn't make sense to expand h as its second order. So we take f of x plus h of x, and we approximate it by replacing f by its a quadratic approximation around the point xt, and we just leave h of x by itself. So all I did between this first and second line here is just replace f of x with that second order approximation that we know that if we minimize that, we would get back the gradient update for regular gradient descent. And I took that and I added to it h. So we're using the fact that f is differentiable here, but we've made no assumptions about h. So there's a little bit of algebraic funny business here. So I'm writing equality signs here, but that's a bit misleading. So the first and second lines are not actually equal. They're equal if you put argmin on both sides. So I took the argmin off because I was running out of space on the slides, and I didn't want to make the font too small. But for all of these equality signs, you have to imagine that there's an argmin out front. So what do I mean? What I mean by that again is that in front of all these things, we're going to imagine that in order to compute the actual update, we're going to minimize them over x and look at the x that actually produces the minimum. So the reason why these two things are equal, if there's this first black line is equal to the second black line, these two things are equal under the argmin, is that, well, this first term f of xt is just a constant. So if we were minimizing this over x, it doesn't matter. So I can feel free to just remove it, which is what I did going from the first to the second line. I also added a term that looks like the step size over 2 times the gradient transpose the gradient. So it's the dot product of the gradient with itself. Again, this is a constant, so under the argmin, it doesn't change anything at all. And otherwise, I just expanded x minus x t, the 2 norms squared, and just rewrote it as x minus x t transpose times x minus x t. So if you sort of expand out all of these terms, collect like terms, and refactorize, you'll see that basically like what this term does, what's the algebraic term for this? This is like what completing the square. This particular term right here, I added in because when you take all these terms together, this is the term that completes the square. Which square is being completed? It's this thing right here, this x minus xt minus the step size times the gradient, the 2 norms squared. So that's the reason for adding this term right here. It's just that simple algebraic trick that you would have done back in, I guess, like algebra 1 or algebra 2, right, where you turn something into a quadratic by adding an appropriate constant term. Okay. So again, I can add that here, right, and still maintain equality under the argmin because that thing is just a constant, right? It doesn't change where the minimum is at all, right? It changes the value at the minimum, but it doesn't change where the minimum is located. So the idea then behind the proximal gradient method is to replace this argmin that basically we got from gradient descent with this argmin, right? An argmin over this last expression here. Okay. Are there any questions about this so far? So this is just the motivation. We'll do some examples in a minute that are a little bit more involved and actually apply the thing. But I want to make sure that everybody sees where it's coming from first, right? We start off with this second order approximation whose minimum corresponds to the update from gradient descent. We then assume that we have a function that we're trying to minimize a function that can be written as some differentiable piece plus some non-differentiable piece, and we're applying the same strategy in that we'll rewrite the differentiable piece using the same approximation, and the non-differentiable piece will just sort of leave as is. Okay. So like I said, the basic piece of the proximal gradient method then is to solve optimization problems of this form in order to produce the gradient update, right? So it's not exactly what you would get with gradient descent, right? It depends on like solving some optimization problem, right? In this sense, it's very much like the projected gradient method or the Frank-Wolf algorithm, right? Where in order to actually compute the next update, we had to solve some optimization problem, right? We couldn't just step from where we were to some new location, right? We had to solve some optimization problem first, right? In the case of the projected gradient method, right, we took a step and then we projected back onto the set of constraints. And in the Frank-Wolf algorithm, right, we actually find a direction to step in by computing the gradient and then solving some linear programming problem to find the best direction to step in within the set of constraints. So same thing here. In order to compute the update now, we have to solve an optimization problem. Granted, this is an unconstrained optimization problem because we're talking about an unconstrained minimization problem, right? But the same kind of reasoning applies, right? We still have to solve some optimization problem in order to compute the next the next iteration of the algorithm. Right. So formally, this is what it looks like. So we define this thing that we're going to call a prox operator, and that it's a function of x and a step size, and it's an operator because this prox thing is a mapping from an n-dimensional vector to another n-dimensional vector. So it doesn't return a single real number. It actually returns a vector that's going to correspond to the update that we're interested in. So all I did to write down this prox thing is I replaced this. I changed x to z and replace this by x. So this is this x is going to be the input to the function. So prox x is defined this way, where that's a z. Oops, and that's a z2. So this piece, this xt minus the step size times the gradient, right? So the actual gradient update, we'll just take as that to be input to the actual function. So in this first expression, right, if I would set x equals xt minus step size times the gradient of f at xt, right, I would get exactly that formulation from the previous slide. Yeah. Okay. So the reason for doing this is just to make it look more like the standard gradient update, and nothing else. So the proximal gradient descent algorithm then iterates the following procedure. It sets xt plus 1 to be equal to the this proximal function applied to xt minus the steps, the gamma times the gradient of f at xt. Okay. So in order to actually compute this update, then, right, we have to be able to solve optimization problems of this form, right, of the function star, right, for basically a fixed x. So the reason to sort of abstract out the xt minus gamma times the gradient of f of xt is, again, it's kind of being treated as a constant in the optimization problem. So we can look at how easy or hard is it to solve optimization problems of this form, because whether or not this proximal gradient thing update is easy to compute or can actually really be applied will very much depend on whether or not we can basically solve the appropriate optimization problem. Okay. Questions yet? So it all looks a little bit fancy, but it's just a bit of algebraic manipulation. I mean, we're literally just taking, all of this work on the previous slides was just to simplify this expression into some form that like makes it look aesthetically similar to the gradient. We wouldn't have had to do any of that, right? We could really have just started from the first line on this slide and written the optimization problem as just argmin over x of that thing. Right? That would have been that's exactly what the proximal update is solving. It's just we want to make it look like the actual gradient update, so we did a little bit of extra algebra, introduced this like prox operator thing that sort of encapsulates the optimization problem that we need to solve, and then rewrote the update in terms of the gradient update, and then applying this proximal operator on top of it. Okay. Questions? It's a bit hard to actually visualize what this thing is doing. Again, the intuition is it's just sort of a different kind of local approximation to the function, where like just part of the function is being approximated with a quadratic, and the other part is being left as is. Right? We saw kind of similar optimization problems to this, right, in Newton's method, right, where we would have solved. We would have made some, local quadratic approximation of the function and then minimized that local quadratic approximation. Again, though, the difference was in Newton's method, right, we would have applied the quadratic approximation to the entire function that we were trying to minimize, and not done this like weird piecemeal thing where part of the function is being approximated, right, and part of it's not. Again, right, the reason for doing this is because we don't want to have to take derivatives of things that are non-differentiable, right? It can create a little bit of a headache, and we know if we do that, it results in slower rates of convergence, right? That's what happens with the subgradient method. Okay, so let's do some simple examples of this. So I have sort of one like example where I coded it up, and I'll show you a visual representation. Before we do that, though, let's do some simple algebraic examples where we pick some different choices for h, and see how it might work. So as an example, well, this isn't quite the example yet. So the proximal operator requires us to solve an optimization problem of this form at the top of the slide. So if h were differentiable, this is an unconstrained optimization problem. So we can just take the derivative and set it equal to 0. Now it's possible, right? If you're, it could be possible, conceivably, right, that h is unbounded from below or something. But the only way that this thing doesn't have a minimum is if h is a somewhat strange function, because this first term, it's growing to infinity as you step further and further away from further and further away from x, so whatever you're applying the function to, right? So as z gets further and further away from that, the first term is going to infinity. So which one of these two terms dominates will determine, right, whether or not this thing can even have a non-finite minimum. But let's suppose it does for the moment, right? If it does, right, we can just take, if h were a differentiable function, differentiable and convex, we have the whole proximal operator is solving our convex optimization problem. So we can just take the derivative and set it equal to 0. And then solve for z. Now, again, right, is the same issue that we would have had with regular gradient descent, right, is that it might not be the case that you end up with a closed form solution for z here, right? It might not be possible to actually solve this equation for z. And if it's not, right, then you'd have to run, gradient descent, by itself just to solve this optimization problem, right? However, right, just like, the projected gradient method, this update will be particularly efficient whenever we can actually solve for z in this expression. Okay. So one other thing to point out that we'll make use of somewhat soon is that, of course, the criteria for being at a global optimum is the same, even if h was non-differentiable, right? If h is non-differentiable, then the criterion would be that I'll put a little partial thing here. H of z. Oh, I don't know. I forgot the notation I was using. Let's put. I'll write an s there. Let me use this notation. S of h has to contain, has to be equal to 0. There has to exist an S of h z, right, where this thing is a subgradient of h at z. Okay. So equivalently, right, for non-differentiable functions, right, you just need that you're at a global minimum whenever 0 is a member of the subgradient, right? So again, like kind of been pictured, right, for the absolute value function, right? 0 is a valid subgradient at this non-differentiable point, right, which means that it's a global minimum. So let's see an example. So here's a simple example. So let's suppose that h of z was a differentiable function, and it's just lambda over 2 times the norm of z squared. So we saw things like this before, right? If problems like this come up all the time in machine learning contexts, right? We have some function we'd like to minimize, and we add to it this function h of z, right? If h of z was of this form, we would call h of z an L2 regularizer. Right? We saw something like this, right, when we were doing the the matrix factorization problems, right? We added a separate term that encouraged you not to pick values that were too large or too far away from 0, and some tunable constant lambda that accompanies them. So this is quite a common thing in machine learning applications, at least. So let's take a look at what happens, or how the gradient update changes, right? If we would apply the proximal gradient method with h given as this essentially L2 regularizer. Okay, so we just take the gradient of this thing, right? It's differentiable, so to solve this prox thing, right, we need to minimize this expression over z. So we compute the gradient, and we get the gradient as 1 over the step size times z minus x plus lambda z. So we set this equal to 0, and then solve for z. So we get what? Lambda plus 1 over the step size times z has to be equal to x, so that z is equal to x over divided by 1 over the step size plus lambda. So then remember that the actual update procedure would set xt plus 1 is equal to prox the step size applied to xt minus step size times the gradient of f of xt. Right, so we plug this thing in for x in this expression, and we get the update that's pictured here. So that was easy, right? And it was easy because this was a differentiable function, right? It's bounded from below. We just compute the gradient, set it equal to 0, and solve. And C has a closed form solution here, which is just the x you spit in times some constant. So if we're comparing that, right? So on the left-hand side here, this is what we get with the proximal approach. And the right-hand side would just be regular standard. This is just gradient descent. Right, so you see that there's a difference in that, right? We don't have to actually compute, the update sort of, I guess, implicitly depends on the gradient of the h piece, right? But not explicitly, right? Because we solved some optimization problem to get the update, right? But we didn't actually, it's not formally, the update doesn't formally depend on that gradient, right? It just depends on the solution to an optimization problem. Okay. So you can see that these two expressions are different, right? They're not the same thing, right? We shouldn't expect them to be the same, right? Because the way that we're traversing through space has been changed, because instead of computing the gradient of all the pieces, we just computed it. We used a second order approximation of the f part, and then solved an optimization problem explicitly, right, over everything else. Okay. Questions about this example? So again, right, we get a nice closed form solution, right, because the optimization problem that's being solved by this prox operator, right, has a closed form solution, right? If it didn't, right, the optimization problem that ends up being solved could be quite difficult. And if that's the case, there's really no benefit to using this, because you'll have to solve a separate a problem that might just might be so expensive in it, just by itself. Any questions about this so far? The next example is going to stretch your mind a little bit, so just because it involves the solving the optimization problem will be a little bit more challenging for the next piece. So I want to make sure that we're all happy with this one first. So you could go, implement this, procedure yourself for different choices of f and see what happens. I didn't do that. I implemented it for the h, the non-differentiable h that we'll take a look at next. So I have, some nice pictures to show you for that. But you could go and do this one yourself too. Okay. Good. So let's take a look at an h that's a little bit more interesting, one that we actually might want to apply the proximal gradient method to. So again, right, this expression is the kind of thing that we would see in machine learning applications, and I think we saw this on one of the homeworks maybe too. So this is a different norm. Right, so now instead of having lambda over 2 times the 2 norm squared, we're replacing it with the L1 norm, which, if you remember, this thing by definition is the sum over all I of the absolute value of zi. So I think this is one of the examples that we had way back in convex optimization when we were doing examples of convex optimization problems. This is an example of a kind of term that we would add if we were trying to encourage sparsity. So it comes up in like what are called lasso problems. So least squares regressions with a penalty like this that's been added to them. Of course, right, because this is a sum of absolute value functions, it's a non-differentiable function. So now, as before, we're tasked the prox operator tells us that we need to solve we need to minimize this function over z for a fixed x. So we take the derivative, right, and this thing is again not differentiable, right? So there's a couple different things that can happen, right? So if we compute the partial derivative of this expression with respect to zi, the first term is differentiable. So we just get 1 over the step size times zi minus xi. But the second term is not differentiable. So if we're differentiating this expression here with respect to zi, well, if zi is greater than 0, we get a 1. If zi is less than 0, we get a -1. And if zi is actually exactly equal to 0, right, then we have our choice of subgradient, right? It can be anything between -1 and 1. So just like before, right, we would set this equal to 0 and solve, right? Although now it's like slightly complicated because we have to solve, right, basically in 3 different cases, right? The case where zi is greater than 0, zi is less than 0, and where zi is between, zi is equal to 0, right? And in that case, d can be any number between -1 and 1. It's this weird thing, right, with the subgradients, right? We have a whole big choice of which actual subgradient we want to pick, right? So there's lots of flexibility here, and that added flexibility just makes it slightly more annoying to solve this system of equations. Now, there are other methods to find the minimums for these prox operators that actually are a little bit nicer than this case analysis, but this is the last class. They're a little bit more complicated. It's really not worth introducing them. Okay. So continuing on, right? So like I said, I want to set this thing equal to 0 then and solve. So it turns out, if we do that, we get the following. So again, it's just a case analysis, right? If we know that, we setting it equal to 0 and solving, we get that zi should be equal to xi minus the step size times lambda times di. And again, we just break it into a case analysis, right? So if zi is greater than 0, we set this thing greater than or equal to 0 and solve, right? So in the case that zi is greater than 0, di is equal to 1, right? That's this case up here. So in that particular case, zi would have to be equal to xi minus the step size times lambda, which of course will be greater than 0 as long as xi is greater than the step size times lambda. Similarly, if zi is less than 0, then it better be the case that that xi has to be equal to has to be less than gamma times lambda times di. But if zi is less than 0, di is a -1. So xi would have to be then less than a minus the step size times lambda. And that's the case. Di is a negative number, so we get xi plus step size times lambda. That's right here. And then the other case, zi is 0, right? And that occurs whenever xi is basically between those two expressions, right between the two things we just took a look at. So that's the solution to this problem. So zi here is it's the argmin, right? It's the thing that minimizes this this expression. So you can plot this function to see that that is indeed the case, right? You can just take a look at, right? Really, you could, everything separates into individual pieces here. So we could have really done this for just a single variable at a time, right? Which is basically what we did. So you could go, plot this to convince yourself that that's exactly what happens. So as x changes, you get different values for z. Okay. Anyway, this is the solution to the prox problem. So and another way of saying this is that prox gamma x, right, is equal to this. Let's put a little star here. The optimal solution that we get from it's just a little bit of a case analysis, right? So it occurs in a closed form here, and that happens even though this is a non-differentiable optimization problem. Okay? It just breaks into a couple different pieces. Questions about this? So that's the solution to this proximal optimization problem. Now, I'd like to show you what this looks like kind of what the effect is of doing this in practice. So oh, that should be a W. I coded up some examples. So just as a reminder of where this would be applied, right? So let's suppose f of w was just the least squares function that we saw on the first homework, right? So that the aim here, right, is to find a line or a hyperplane that goes through comes as close to a collection of data points as possible, right? At least in a squared error sense. So if we add this, if we choose h of x to be lambda times the norm of w1, what we get is basically a sparsity encouraging regularizer that we call L1 penalized regression. And sometimes in this particular case, this gets a fancy name. It's called lasso, which is also actually pretty popular in statistics for feature selection stuff. So if you go on and take machine learning or statistics class in the future after taking this course, you'll likely see this expression again. So if we look at what the difference between the two updates is, that if we would solve this with the proximal method, right, we would get this update that's at the top of the page, right? That's the actual proximal update. We would set this thing equal to xt plus 1 and iterate. If we were solving this with subgradient descent, right, we would do something like the second line, right? We would just compute a subgradient of the function at the point x, t, Oops. So that's an xt. Subgradient the function at the point xt, right, which is just this, right? We just look at the sign of the elements of this vector multiplied by lambda. Right? That's a valid subgradient. That's what we would get with a subgradient update. So again, these expressions are quite different, right? If you just sort of plug them together, you can see that like they're similar, but they're shifted a little bit depending on the actual choices of the step size and all kinds of things. Okay? They're not exactly the same expression, even though they have a lot of similarities, right? Because they're both basically formed from computing gradients of h, except one just uses the gradient of h and the other one solves an optimization problem. So here's an example of what this looks like in practice. So I picked a simple function just to illustrate it. So let's suppose that f was just x1 squared plus x2 squared, and h was just the absolute value of x1 plus absolute value of x2, right? So here, lambda is equal to 1, for the, in this regularizer. It could have been times lambda, but I just set lambda equals 1. Again, just to keep everything, just to keep it, a simple example. So what I plotted here in the figure is the contour plot for this function, f plus h, right? You can see it looks kind of like what we would expect, like it's like a paraboloid, but with sharp corners, right? Like these sharp corners here, right, are coming from the absolute value function. So what's being plotted here is the subgradient method, okay, with a diminishing step size, 2 over 2 plus t. In fact, if you run this without the diminishing step size, it does not converge, right? As is typical of the subgradient method, right? You need to have this diminishing step size rule if you really want to guarantee convergence to the global optimum, right? Because, right, the subgradient, right, may never actually be 0 depending on how you pick it, right? So the optimal solution here, of course, is just 0. That's where the minimum is. And when you run the subgradient method, once you sort of get in the right region, you just bounce back and forth around the minimum, kind of slowly converging to it. I think I ran this thing for about like I want to say there's like 50 to 100 iterations when I'm producing the plot. And I think at that point, the value of x1 and x2 were something like 0.09, like roughly. Like it was getting closer to 0, but it wasn't quite there yet. And I said that's like after 50 or 100 iterations. Compare that with the proximal gradient method. Oops. For the exact same function, which has a very different looking curve. So here I applied the proximal gradient method with a fixed step size, gamma equals 0.1. You don't need a diminishing step size here. In fact, the proximal gradient method behaves a lot like regular gradient descent. So you only need to have a diminishing step size for regular gradient descent if things are sort of are not twice continuously differentiable. The function f, though, is twice continuously differentiable. So it turns out that the proximal gradient method doesn't need a diminishing step size here. And in fact, if it looks like what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, or 15 steps, it in fact reaches x1 equals x2 equals 0. In fact, I just ran it for a fixed number of iterations, but after about 15 iterations, it was at the optimum. It was actually exactly at 0, 0. And you can see sort of, that there's a real difference here, right? This thing never even overshoots the optimum, right? I mean, part of that's just a little bit of a, lucky chance, right? But the other, part of that is that it's not like the subgradient method, right? In that, it's not going to, it doesn't require this diminishing step size in order to get, to make sufficient progress, right? So as it gets closer to the optimum, the the effective amount that you're stepping gets smaller because the norm of the gradient gets smaller. So again, I encourage you, you can go home and, you can code it up yourself. So in fact, if I, add a little bonus assignment, I might actually have you do the proximal gradient method for a different h function. But yeah. So questions about these two pictures? Right. I hope that you can see sort of, oops, you can't really see anything there because there's too much ink. Right. I hope you can see sort of like that at a high level, these things are very different. From a theoretical perspective, the proximal gradient method has basically the same kind of rated convergence as the gradient method, whereas the subgradient method, again, right, like is worse by like a square. And you can see that even in this simple example, it makes a huge difference, right, basically in how quickly the method is converging to the global optimum, even for this incredibly simple function that we would never really even apply gradient methods for. Okay. Oops. Yeah. There's a couple other things to say about the proximal gradient method. Well, I mean, there's lots of other things we could say about it. The reason for introducing it is because actually it's a nice generalization of both gradient descent and projected gradient descent. So as an example, if we choose h of x equals 0, right, then the proximal operator solves this optimization problem. But this optimization problem is trivial, right? Because if our goal is just to minimize the difference between z and x over all choices of z, well, the solution is just, of course, set z equals to x, right? There's no constraints here, right? So if h of x is just equal to, or h of z, if you were plugging in this expression, is equal to 0, right? There's nothing to do, right? We basically just return x. So then the proximal gradient update would then take xt plus 1. It sets it equal to the proximal operator applied to the regular gradient update, but then it just returns that thing. So in this particular case, if h of x equals 0, we just get back regular gradient descent. And it makes sense, right? The regular gradient, when h is 0, the optimization problem we're solving is exactly the same one that was being solved by gradient descent. Right? There's no h term, right? We do this second order approximation thing. We take the derivative, set it equal to 0, and solve, and we get back exactly the gradient update. Right? That's how we constructed it to begin with. So gradient descent is a special case of the proximal gradient method. It turns out projected gradient descent is also a special case of the proximal gradient method. So here, if we let h of x be the indicator function for a convex set C, so what I mean by that is it's equal to 0, h of x is equal to 0 if x is in C, and it's equal to infinity otherwise. Then the proximal operator, which is, in this case, is this expression, right? We want to minimize over z of this norm square difference between z and x, plus this, oops, I changed my notation here. This is supposed to be indicator function of the convex set C applied to z. Again, the thing is either 0 or infinity, depending on whether or not x is in C, right? So we can reformulate that as an optimization problem, right? We know that the minimum can never occur when z is not in C. So this is equivalent to just minimizing z minus x squared, z minus x squared, the norm squared, right, subject to z being in the constraint set C. Right? The constants don't matter here, right? We could put a 1/2, or we could leave the 1/2 times the step size. It doesn't matter. It doesn't change where the argmin is, right? It changes the value of the minimum, but not where it's located. So solving this optimization problem, then, right? We've seen this optimization problem before, right? minimizing the difference between z and x, the 2 norm of that squared, subject to z being in the a convex set C, right? We gave this specific name. We called this the projection of x onto the set C. I mean, it's effectively finding the closest point in the constraint set to the point x. So if we applied the proximal gradient update, then it tells us we should set xt plus 1 equal to the prox operator applied to the standard gradient update, which is just equal to the projection of the standard gradient update. So both gradient descent and the proximal gradient method gradient descent and the projected gradient method are both special cases of this proximal gradient descent procedure. So again, right, this is only particularly efficient if you can actually compute that projection, right? If you can't, right, solving that separate optimization problem, right, can be, just as expensive, right, as, essentially solving the original optimization problem. Okay, questions about any of this? No questions today. Everyone's done with the semester. You've mentally finished the semester already, and it's just time to move on. Okay, why don't I ask you a question, and then we'll call it a class. Is the can I combine these two slides essentially? Let's suppose that I wanted to solve a constrained optimization problem, but let's say with like an L1 penalty, right? So let's suppose that I have some function f, and h was just lambda times the L1 norm of x, and I want to minimize this subject to x being in some constraint set C. Can I apply the proximal gradient method to do this? So this is a constrained optimization problem now, right? Sort of like what's on this slide. Can I solve this problem with proximal gradient? And if so, how would I pick the h? Sure. This one isn't as useful, I don't think. Thoughts? So I mean, if we were to solve an optimization problem of this form, we could of course use the projected subgradient method, right? Right, we compute a subgradient, right? We take some step in the direction, then project back on. Yeah. So we have one proposal. We choose h to be the L1 norm plus the indicator function, right? So if we picked h of x equals lambda times the L1 norm of x1 plus this indicator thing for the set C, Yeah, absolutely. Of course, you can do that. And when we do, right, all that does is add, you know, plus h of z term uh, to this expression. So this will no longer then be it will no longer be the projection, right? It'll be, you know, compute the argmin of this thing plus h of z. So yes, absolutely you can, right? Again, whether or not this is an efficient strategy will very much depend on how easy or hard, right, it is to actually solve this particular optimization problem, right? The difference again though is that the difference between this and like a projected subgradient would be that this subproblem we're solving here in this particular case is not a projection, right? It's something else, right? It takes this h of z, it adds to it something that looks like a projection. You still need the 1/2 there here. Add something that looks something like a projection, but not quite, right? Because it's not, you know, it's not using the gradient information for the piece that depends on h. So there's lots of other kind of neat things you can do with proximal gradient descent. And there's sort of like whole interesting families of optimization procedures that are essentially built on top of these proximal gradient methods. We've not really seen any of them in this course because they're sort of fancier things that come up in sort of really specific settings. But you know, it's a sort of nice generalization of both the gradient and the projected gradient method that sometimes can be quite efficient in practice, right? Like we saw from these previous pictures, right? There's a real benefit if you could actually solve that optimization problem in closed form. There's a real benefit to doing this. So anytime you have like an L1, you know, regularization, right? Instead of applying a gradient descent method, you might, you know, consider applying the proximal gradient method instead. Right? It has better rates of convergence. Okay. Good. Well, I think that's a good place to stop for today. Are there any questions about today's lecture or homework or anything like that?